Let's finally move on to my presentation today. It's my honor to present the Provost lecture series. It's the first time for me to do it. And I chose to talk about one specific research topic in my group on the use of the mechanical force to make new materials and to enable new chemical reactions. Before I start talking about research, let me give a bit of the history of my research group here at OIST. So my unit is called Coordination Chemistry and Catalysis. For those who are non-chemists, this implies that we essentially prefer to use metals for most of our research. So we came to OIST in May 2015. Lab 3 building was just finished. And well, there was no electricity in the lab. And by that time, 1 month later, we got electricity. Together with that, I got my first GSPS postdoc, Orestes. So my group looked like this, 2 people, more or less. But 1 year later, I could assemble the whole group. So I already had several intern students, my first Italian intern in the group, and my first PhD student, Sebastian, postdocs, and a technician. So it was already a full group ready to start the research. My lab was also changing over this time. Okay, so before I move on, let me introduce. This is my current group. So this is during our group lunch at Orange, where we usually go. And well, now you see the group is even growing bigger. So what about the lab, right? So when I came, the lab looked like this. So it was very much empty, but very clean. So OHS was extremely happy. Several months later, it was not as clean, but it was a fully working synthetic chemistry lab already. And the fun part here at OIST, coming to an empty building, was to actually observe how it's being populated by all the instrumentation. When we came, there was essentially no instruments that we could use, more or less, as a synthetic organic group and organometallic group. So I could participate and observe all these events of instruments coming in this flowery carpet packaging and being unpacked and installed, the NMRs and X-ray, EPR, and everything that you need to use. And now I'm happy that other chemistry groups also have access to all of this equipment here, and we work as a fully functioning lab, and we have a very strong instrumentation in chemistry. So anyway, we were ready to start our research, and we started developing several research directions in the group. And I'm not going to talk about all of them simply because I don't have time. The oldest one was on building multimetallic chains, where we use special ligand platforms that would connect several metals together in a chain. We want to study the interactions between the metals, the bonding, and also cooperation between multiple metals to break chemical bonds. The second general direction is on the use of transition metal catalysts for various organic reactions. So, and more recently, we focus on introducing fluorine into organic molecules, or also on carbon-fluorine bond breaking. But today I chose to talk about something that may be a bit closer to the general audience. So I want to talk more about how we chemists can use chemical force to make new types of materials or to enable new chemical reactions. So I'm showing you these 2 ancient tools of mechanochemistry, the field that studies how we can enable chemical reactions through the mechanical force. And in the recent literature, some people even argue that mechanochemistry is older than the chemistry, because the first mechanochemical protocol in the literature, recorded literature obviously, can be traced back to 4th century BC in the work of the Greek natural philosopher Theophrastus, who described this amazing procedure for the extraction of the metallic mercury from cinnabar by grinding it in a copper mortar with a copper pestle. So pretty much specific procedure. You can be sure that in mechanochemistry, people do very thorough literature search, because this reference was traced all the way through the centuries to the work of Pliny the Elder and the alchemists like Zosimus of Panopolis. And then it was cited in the 20th century and the 21st century. So you can be sure if Theophrastus would appear on Google Scholar, he would probably have a very high H index by now. So this is one way to use force in chemistry, very much brute force. And then you do a chemical reaction by grinding. But of course, there may be more subtle applications of the force in chemistry. And specifically, I want to show this curious phenomenon that's called tribioluminescence. Of course, it's been known for ages, but in Western recorded literature, it's been described in the work of Francis Bacon in 17th century, who wrote that the crystal of the hard sugar, when it's broken in the dark, can emit light. It took several more centuries to actually record the spectrum of this emitted light in a later work using sucrose. And a different implementation of this phenomenon is through the use of this particular type of candies called wintergreen. So they contain a wintergreen oil, which is fluorescent. And when you crack those candies with pliers, for example, you can also see emission of light, but that is a bit easier to see because it's activating also the fluorescent oil present in it. And actually, this is a very complicated phenomenon. As it turns out, it's accompanied by emission of electrons, the positive ions, and even radio waves. So we were interested in these general fields of using mechanical force or mechanical action to either enable chemical reactions or to create the materials that would change their properties in response to the mechanical activation. So I'll start with this first project. And this is the team working on this, staff scientist Ayumu, postdoc Daniel, and two PhD students, Tatiana and Mitsuyuki. So we were mostly interested not in hard materials like crystals of sugar, but in soft materials. So we wanted to make soft materials or polymers where we would use the energy provided by mechanical force to activate certain bonds, to cause changes at the molecular level, and that would result in a certain signal that we can detect. And in polymers specifically, that is often done through this approach. You need a small molecule which contains some weak chemical bonds. Then you incorporate into the polymer chain here, and then, for example, you can stretch the polymer that breaks the chemical bonds, activates the mechanophore, and causes changes in the properties like transient emission of light or changes in the color. And when we just started working on this, this field was very much heavily dominated by purely organic systems, where you need to break the covalent bond to achieve the effect. But again, because my group is called coordination chemistry, we wanted to use the metal and develop our own metal-based mechanophore. Before I came to OIST, I was working with this particular ligand. We simply call it N4, obviously because it has 4 nitrogen atoms. And in metal complexes, it tends to adopt multiple conformations, so various different shapes. And this is an interesting property. So the next idea was very simple, maybe even too simple. Why don't we attach this ligand through these 2 points on the nitrogens to the polymer chain? We introduce the metal and then we stretch it. Would we be able to affect the properties of the polymer sample that contains this metal complex? So we started working with this system. We had to screen a few metals before we found the right one for us, and that was copper. Copper is cheap, it's abundant, it's very easy to work with. And copper complexes had a number of good properties that we were looking after. So one of them is that when we make copper complexes with this ligand in model systems, we see they are actually very dynamic, very fluxional. So in solution, they easily change conformation. So these nitrogen tails are basically just wiggling up and down all the time. How do we know it? Because we can record the NMR spectra at various temperatures, and this dynamic behavior and exchange results in a signal broadening. Now, the second interesting property of these complexes, they are photoluminescent. But not only that, their photoluminescence was dependent on how rigid or fluxional they are. So by using different structures and different substituents, we can control how fast this exchange is, how quickly this nitrogen tail wiggles up and down. And we noticed that when the system is more rigid, then we obtain brighter emitting complexes, so photoluminescence quantum yield is increased. And when systems are more fluxional and dynamic and exchanges fast, then photoluminescence quantum yield goes down. So then, of course, this can be explained typically in literature regarding copper complexes through the suppression of the non-radiative decay, which typically involves this kind of dynamic behavior and structural distortions, for example, through Young-Taylor distortion through coordination of an extra ligand, and we just have this extra nitrogen tail sitting just around our metal. So this probably is the reason for this effect. So the next step was we attach it to the polymer and try to stretch it. And this is how we make it. I will not talk too much about this. The films are essentially photoluminescent, and that's all we need to know for now. So what we do next, we stretch the films in the tensile stretching machine, and we record the photoluminescence intensity. So we see as we stretch it, so this is the degree of stretching, this is an increase in the photoluminescence intensity. But also as we release it, it decreases again. And this can be repeated through multiple cycles. So this is the experiment repeated for over 30 times. This is essentially how much patience Ayumu had to keep repeating this measurement. And very conveniently, we can also do it through the CCD camera. So this is actually gray color. The colors here are relative colors. They reflect the intensity. So when we stretch the films, the photoluminescence intensity gain increases, and when we release it, it decreases. And this is done on a millisecond time scale. So with this, and actually this result was also highlighted on the chem station, we could claim that we developed our own special type of metal-based mechanophore for mechanoresponsive polymers, which is based on the dynamic behavior of metal complexes, especially photoluminescent metal complexes. This does not require any covalent bond breakage, so the response may be very fast. So this is one approach to make a mechanoresponsive system. What's the other approach? Well, I mentioned this phenomenon of triboluminescence before, with Francis Bacon describing light emission from the cracked sugar. So how about triboluminescent materials? And that would mean that we emit light directly in response to the mechanical activation. So the practical implications is very simple. You don't need an external excitation source like you need for photoluminescence. And in triboluminescent materials, most studies have been done using crystalline materials. And the dominating theory was that in crystalline materials, when you break the crystal, you fracture it, and at the crack point, you generate in unsymmetrical crystals oppositely charged surfaces. And if thus generated electric field is strong enough, this may lead to the excitation of the surrounding gas, so essentially the gas discharge. And those lines you saw with the spectrum recorded upon breaking sucrose was actually discharge of the nitrogen gas. So this is one model to explain, and actually there are many exceptions to it as well. Another possibility, if your crystal, for example, already contains a luminophore luminescent compound, this event may also directly or indirectly excite that luminophore as well. And this project showed us that actually serendipity is very important in research. So when Ayumu was working on model systems, he noticed that when he grinds the complexes in the vial with a spatula, they actually emit light. So they are all triboluminescent. You can crush the crystals between two glass plates, and you see this flash of light. Or this is really the same event, but recorded with help of some collaborations with a high-speed camera. So these are triboluminescent compounds, which is a very nice property to study. But the strange thing was that almost all of our complexes were triboluminescent. That's actually unusual because this property is very tricky. It's hard to predict it, and it's very much dependent on the crystal structure. And here we see it in the whole series. This gave us an idea, although it's not directly related. Maybe we should try and translate this property from the crystalline state to the amorphous state. And then what we did is that we blended our complexes in the polymethyl methacrylate in low amounts, and we make the film. Then when we rub this film under argon, in this case, with the glass rod or the silicon rubber rod, we see the light emission in response to this activation. Again, we confirmed that the films were actually amorphous. We don't have any evidence of the microcrystalline phase present here. And almost all of our complexes showed triboluminescence in the polymer films. This is how the photoluminescence of the copper complexes in the films looks like. So this is how the triboluminescence of the same complexes in the films looks like. What's the difference? Well, this set of lines here, very sharp lines. And if you remember that spectrum of the cracked sugar light emission I showed before, so these are essentially the same lines. So this measurement was really performed under nitrogen gas, and they belong to the discharge of the nitrogen. And this gave us some idea about the possible mechanism of why we see this triboluminescence in the polymer films, which are amorphous. Most likely it involves the triboelectrification of the polymer matrix when you rub two dissimilar plastics against each other. So more like a static electricity build up when you rub the wool against the balloon or the styrofoam. So in all of the cases, we see that we have certain gas dependence in our triboluminescence in the film. So we can use different gases and see a different set of lines corresponding to the discharge of these gases. Actually, even if we don't have a copper complex, we can also detect the gas discharge lines just by rubbing one plastic against another, which is not surprising, but they are very weak, so they are very hard to see by a naked eye. Of course, we can detect it by a spectrometer. But when we introduce the copper complex, then this emission in the visible becomes much brighter and much easier to see. We can also make the films that would show it even under humid air in Okinawa, which actually is a big problem to see the triboluminescence. So what's the good news and what's the bad news? It may come as a disappointment for us as coordination chemists because it looks like this property does not require any metal participation. But the good news is that it makes it much more practical. So now we can make triboluminescent films containing all the variety of the luminophores that we can find on the shelf, organic compounds, copper complexes, iridium, europium, whatever you can choose, and we can create all this multicolor emission under different set of conditions. So this was much easier to use now. But then in more recent studies, we want to answer the other question. So all of this is done in the polymer films. But luminescent compound is actually one of those shown here. So do we need a polymer matrix at all? And this is what we've tried to answer in our more recent work. And Ayumu in my group, he initiated this study of looking at a series of copper complexes. And one question we wanted to elucidate is that, well, what's the relationship between triboluminescence in a crystal phase and in amorphous phase? So we found that if you look at the crystal samples of the series of complexes, some of them are triboluminescent and some of them are not. This is not unexpected. This very much depends on the crystal structure. It's difficult to predict. You may find some trends, but not very clear trend. So what about amorphous state? How do we make it? With the help of a postdoc in our group, Daniel, we made amorphous films by spin coating containing these copper complexes, for example, simply on a glass slide. And they are amorphous. We can see it from film XRD. And surprisingly now, essentially all of the complexes we've tried were mechanoluminescent in the amorphous phase. So this is somewhat contrary to the expectations, where most of the studies are heavily focusing on a crystal state, whereas we can see that triboluminescent is much more predominant for us, at least in the amorphous phase. And it's much easier to observe as well. And we even see triboluminescence in amorphous phase when it doesn't show up in a crystal state. So this was the unusual part here. So this is a very spectacular phenomenon, almost like a little lightning here. We can see it by rubbing. We can do it directly. We can do it through the layer of a completely inert film like PVC. We can also do it by twisting and peeling off and contact separation and different types of activation. So with this, let me summarize the first part of my talk on making mechanoresponsive material. In our group, over these past several years, we've developed two approaches to make mechanoresponsive materials, and they complement each other. So one is based on the dynamic behavior of the photoluminescent metal complexes that we incorporate into the polymer. That allows us to very quickly see very fine changes in the photoluminescence intensity in response to stretching on a millisecond timescale. Now, the complementary approach would not require to have external light source. There, we would use a mechanical activation, for example, rubbing, twisting, and contact separation to emit light directly through the mechanical activation. And the interesting discovery here, I believe, was that we found that actually it works very well in amorphous state, and crystalline phase is not required to see it. So with this, finally, let's move on to the second part, actually the cooking type of chemistry. So we always want to use our chemistry for enabling new chemical reactions at the end. So can we use a mechanical force for this? Well, we can use one of these tools, and mortar and pestles have been used for centuries by chemists and alchemists. We could also use a hammer, a very simple tool. Actually, even these days, you can find research papers published where mechanochemists would use a hammer to punch their reaction mixture 100 times to achieve the result. Well, we didn't have enough patience or strength to pursue these attempts. So we decided to choose something that's slightly more modern, like this instrument. It's called the ball mill. So what's the ball mill? It's a simple machine. It has two arms. And there you have two jars, like this one. So in a jar, you put your reagents, maybe a drop of solvent to help mixing, and one or several balls. Then you close the jar, then you fix it here in these arms, and the instrument starts shaking from side to side at a high frequency, 30 Hertz, for example. That's what we usually use. And the balls inside, they fly around because there is some headspace, and they hit the walls, create a significant impact, and that grinds the whole reaction mixture and enables very fine mixing. And it's a very popular instrument in material science, usually used to grind samples, but now becoming also popular in chemistry. So the first team working on mechanochemical reactions in my group were the intern from Kazakhstan, Valeria, and the student, Shubham Deolka. And Valeria ran the first reaction. She worked with some metal complex, she put it in a ball mill, and she grinded it. We opened it, and we noticed everything just got reduced. We didn't understand what that means, but that was her last week. Actually, now, going back to this, we totally understand this result. And the current team working on this project is this Austrian PhD student, Thomas Hazeweder. Unfortunately, he is not here right now, so very dedicated, hardworking, and smart student. And also our team was joined recently by Ekaterina, technician, and the rotation student Leo. So these three people are now developing the mechanochemical direction. And when we just started working on this, we had a specific point of interest in this field. So we wanted to make fluorinated organic molecules. And why is it? Well, actually, they play a very important role in the pharmaceutical market. So many known drugs or drug candidates contain fluorine in them. And this is because this may alter lipophilicity of these molecules or their ability to cross the blood-brain barrier, or also make them more stable towards the metabolic degradation compared to the non-fluorinated analogs. And we already had some experience doing trifluoromethylation in our lab, but using classical solution-based methods with some metal catalyst. And when we just started working, we noticed there was one very interesting report on a mechanical approach to trifluoromethylation. This was reported by the group of Hajime Ito and Koji Kubota. And what they proposed is that they use Umimoto reagent to trifluoromethylate arenes or heteroarenes, and they use this very special additive, barium titanate, that they put in a reaction mixture. So what the proposal was that this mechanical agitation in a ball mill deforms this particle. And when you create a polarized particle, this may act as a charge transfer catalyst and cause the single electron transfer events, accordingly initiating the whole reaction. And we thought that maybe this protocol is not the most suitable for us. Umimoto is expensive, barium titanate is not cheap, and by that time we had our own preferences in trifluoromethylation. In particular, our favorite reagent was really Tony reagent. So there are different types of Tony reagent. We just use this particular one. Why is it good? Well, first of all, it's several times cheaper. But it's also good that it's available in many different forms. So you can buy one which contains trifluoromethyl group, or you can also get the derivatives that would have some other fluorinated alkyls. So it's very modular. So we started to work on mechanochemical trifluoromethylation of arenes and heteroarenes. Now I have to say, so this Tony reagent, this may actually come in two different forms. So you can buy it just as a pure reagent itself, or you can buy it with the zeolite. So it's essentially Tony reagent mixed with zeolite. This is done for safety of handling, transportation, and zeolite is a kind of absorbent that's used for some chemicals. So Thomas, who was doing these experiments, he was very careful, and he noticed one interesting thing. He had totally different reactivity when he used Tony reagent itself, pure reagent, or the one that was mixed with zeolite. And surprisingly, actually, it was more active with this, as we thought, inert filler zeolite. So what is actually zeolite? And that's how it looks in SAM. So it's a commercial name of the diatomaceous earth product. And it consists of the fossilized remains of the diatom, or microalgae that's been sedimenting for millions of years. And for us as chemists, we often use it as a filter aid, assuming it's inert. So we have a fine suspension, it's just filtered through zeolite. It may be used as absorbent for other applications, but the advantage is it's very earth abundant, cheap, and more or less a green reagent, but we don't see it as a reagent, by the way. And also it looks beautiful in the SEM with all these amazing structures. So we found that with zeolite, which everybody thinks is totally inert, actually is a real activator of the mechanochemical trifluoromethylation. And it only applies to mechanochemical conditions. It offers many practical advantages because zeolite is cheap, and it's non-toxic, so it's very much earth abundant. It's easy to get, and it's not just zeolite we had success with. We could also achieve similar results if we worked with iron oxides, also amazing activators, and even something simple like magnesium oxide. And then I told Thomas, you should go and collect some sand from the beach. So Thomas did it. He went to the beach and he collected some sample of sand. And if you know Okinawan sand, it's actually mostly coral sand, a biogenic sand. So it consists mostly of calcium carbonate. And even sand from the beach was a good activator for this reaction, which was a really economical approach. So saving us a lot of money if we can just use the sand here. So we had some ideas how it works. We proposed some hypotheses. We proposed that iron may be involved in the reaction because we had a lot of success with iron, but we didn't fully understand the mechanism at that point. But we published our first paper where we reported this very practical and cheap protocol for mechanochemical trifluoromethylation. And Thomas created this amazing cover art for Angewandte where he depicted the ball mill sitting on an Okinawan beach surrounded by beautiful diatoms and thinking about doing trifluoromethylation. So what would be the next step, right? Well, we could potentially screen different additives, something apart from zeolite, or we could screen different reactions. And we were working on both of these directions in parallel. When we started screening various additives, my lab almost turned into an alchemical lab. We would throw something like a mix of shells and bones and sprinkle it with a volcanic ash from Sakurajima. Some of these additives worked, some of them didn't. It was completely inconclusive. And then we were expanding the scope of reactions, where this is where exactly we had more success to explain the result. So we focused on this particular reaction, and this is the carbon-nitrogen cross-coupling catalyzed by nickel salts. This is a very useful reaction for making amines. And again, Thomas found that it works amazingly well with zeolite. But that actually is very strange because nickel bromide that we use here as the catalyst is not really a catalyst, it's a pre-catalyst. So it's a precursor which you first need to reduce to nickel in low oxidation states like nickel 0 or nickel 1 to enter the catalytic cycle. So what is the reductant here? It's definitely not zeolite because if you have something that's sedimented millions of years ago, it's very unlikely to be a strong enough oxidant to reduce nickel pre-catalyst. So we looked at this reaction more closely. For example, what happens if you don't have an additive? We just mix reagent and ball mill it. Well, it's not very efficient, the yield is extremely low. Now, if we add sealite, the yield goes up dramatically, extremely efficient. But it's not just sealite. We can also see increase of the yield with barium titanate, piezoelectric material, with magnesium oxide, non-piezoelectric material. We can even use the diamond powder, and we can use tungsten carbide. And actually, there is nothing in common between all of these materials. And it's very unlikely that they may act as a strong enough reductant, with some exceptions, for the nickel catalyst. So what's actually going on in this reaction? We decided to investigate it through the help of the TEM and our collaborator, Alec Lagros, from the core facilities. So we looked at the sealite particles before and after the reaction. So I have to say, sealite itself naturally contains a little bit of iron in trace amounts. But after the reaction, we found a big difference. So of course, we still have silicon and oxygen naturally present, but after the reaction, we see these little patches where iron and chromium are co-localized. And chromium definitely was not present in the reaction initially in sealite before the reaction. So where does it come from? And I suppose by this time, the majority of the audience already could guess where it comes from. When you have a co-localization of iron and chromium, this is actually another representation of this. So you see again a thin layer covering the sealite particle with iron and chromium co-localized. So the setup that we use to run the reaction is this. So we have a jar and balls, and they may be made of different materials. Would it be tungsten carbide, zirconia, or stainless steel? Stainless steel is the cheapest one. That's what we use most of the time. And that's exactly where iron and chromium tend to be co-localized. And we actually confirmed that because if we check the electron diffraction pattern with this little coating on the sealite particle, we see the pattern that we expect from martensitic steel that is used in these jars and bowls. And it doesn't happen just to sealite. It basically happens to any solid insoluble additive that you add into the mechanochemical reaction mixture. So the same thing happens with magnesium oxide. You again have these patches of iron and chromium. Same happens with a very popular reagent, barium titanate. It also gets covered in iron and chromium. And finally, that explains our mechanism. So what's the actual reductant for our nickel catalyst is most likely the zero-valent freshly exposed iron or a zero-valent chromium present in the steel that reduces our nickel catalyst and activates it towards entering the catalytic cycle. So this is the main conclusion from this current work, that in mechanochemistry, we cannot ignore mechanical phenomena like abrasion. Abrasion happens, and it always happens. Actually, even if you don't use any solid additives, it also happens, just to maybe less extent. But you must take it into account because that may affect the mechanistic interpretation. So not only in mechanochemistry, but in any chemistry, we always need to remember that our reaction vessel may not be innocent, as we believe. And I'll show you some examples of this later. And actually, our TEM study demonstrates this is not a simple process. It's not just we abrade it and generate some iron particles. We actually cover our sealite or magnesium oxide or barium titanate with a layer of the stainless steel. And you can imagine, all these additives are commonly used in mechanochemical reactions. And if they are redox active, actually that might totally change your mechanistic interpretation of what really happens there. And this actually takes us back to 4th century BC to show how chemistry is connected through all this time. Because you see in this procedure of Theophrastus that he used a copper mortar and copper pestle. And as historians mention, in this ancient procedure, it's very hard to know which part of that is important, which is not. But luckily, more detailed studies were performed recently, in particular in this work by Italian authors. So collaboration between historians, philologists, and chemists, where they try to study this process. And cinnabar that was used as a precursor is actually mercury sulfide, and a copper that was present in a mortar with a pestle is actually the reagent. So Theophrastus had the same observation as we are having now, along with some other groups, that sometimes your reaction vessel becomes a reactant. And interestingly, in those ancient times of the alchemy with Zosimus of Panopolis, people did even a very similar control experiments trying to replace copper mortar, for example, with different metals like tin and lead. So very much that shows that we all use the same approach. But I don't want to finish just at that point, because even though it's very important to remember, but it almost sounds like a trivial thing, right? So, okay, you need to remember your reaction vessel may not be inert. Is there any good consequences of this? So I want to finish at a different example. That's from 20th century, and it relates to the discovery of the Ziegler-Natta catalysts that are now used for the multi-million-ton production of various plastics, high-density polyethylene, stereoregular polypropylene, and so on. And the history of this discovery is very important. So on the way to discovery of this catalyst that were, actually later Ziegler and Natta received the Nobel Prize in 1963, the doctoral candidate of Ziegler, Hulskamp, was running the regular reaction that he found, and he was studying oligomerization of ethylene, really looking for oligomers. So in one of the reaction mixtures, he found that the result was different. He almost exclusively got 1-butene, a very short product. And this wasn't the product that he wanted. So they could as well discard this result, but they didn't. They performed a strenuous investigation of what's going on in this reaction mixture. They figured that this result and this totally different outcome was due to the catalytic effect of the trace nickel metal that was leached from the walls of the steel autoclaves that they used. But again, they could just stop at this point because they were not after 1-butene and just resort to cleaning their autoclaves better. But instead, Ziegler decided to investigate in detail why such trace amounts of transition metal may such greatly affect the reaction outcome. So Ziegler initiated a systematic study of the effect of various metal additives on the reaction outcome, and this led them to the discovery of titanium and zirconium that form the basis of the modern Ziegler-Natta catalyst. So what I want to say is that it shows that in chemistry, so many factors are important. You need to have a bit of luck. You need to have some serendipity. Very important to have observation skills, of course, notice what you see around. And more important probably is that, well, you need to plan your experiments in such a way that not only you see the result that you want to see, but sometimes you also expect to see what you didn't want or didn't expect. But in addition to that, and you need to make one step forward, decide what to do with it by asking a good question, and that may lead you to the discovery of the new catalyst, as you can see from this example. So let me finish on this cheerful note, and I'd like to thank my research group. So very hardworking, dedicated group. So they really generated all of these results that I'm showing you today. I want to thank our collaborators from the core facilities. So many of them contributed to our work, measuring crystals, helping with imaging, NMR, STM. And of course, I would like to thank OIST for generous support, as well as the GSPS grants that we obtained in our group. And of course, thank you all for your kind attention today in coming to this lecture. And I'll be happy to answer any questions.